Okay, so today we're going to continue working with our function families. In our first couple of lessons, we looked at linear functions, exponential functions, and quadratic functions, the ones that we had already learned about, and reviewing those. In this lesson, we're going to look at a new family of functions, which are the absolute value functions. So in this lesson, we're going to see, well, what does a graph of an absolute value function look like, and how can I transform it? And you should start to notice some patterns with the lessons that we've already done, because the transformations all work in a very similar way. So for our do now, let's just review some basics about absolute value graphs. So it says, complete the table of values for the following equation, y equals, now remember these two bars right here, these straight bars, those are for absolute value. Now, if you remember about absolute value, which I know you learned about in at least 6th grade, if not before that, is that formally the definition of an absolute value is the distance something is away from 0 on a number line. What you guys like to remember absolute value as is that it is always positive. So if I look at this table right here, if we try to find the absolute value of -2 as our x value, the y value would be +2. If we found the absolute value of -1, that would be +1. The absolute value of 0 would just be 0. The absolute value of 1 just stays as 1. And the absolute value of 2 would just be 2. Now let's see how we can confirm this table of values using our graphing calculator. So if we go to an online graphing calculator, you would go to y equals. Now to get your absolute value bars, if you notice in the lower left-hand corner underneath the X button and above where it says ABC, you see the little A with the 2 absolute value bars. So you're going to click that and you'll notice that the 2 bars pop up. If I just want the absolute value of X, I would just type in X. And there you see what our graph looks like. So what you'll notice now is that an absolute value graph is always going to be in the shape of a V. We can still call this point down here 0, 0 our vertex or our turning point, just like we would do with quadratic graphs, except instead of quadratics where they're shaped as a U, now they're going to be in a V shape. So just so that we get an introduction to that, we now know that an absolute value graph is going to be in the shape of a V, where the vertex happens at 0, 0. So let's get into our lesson here. Again, now that we know what the basic graph looks like, we're going to talk about transforming it. So for this lesson, you're going to need the new packet function families part 2, and we're starting on page 1. So for these functions, our parent function or our original absolute value function is just y equals the absolute value of x. When we start to transform it, it's going to look pretty similar to our quadratic functions. We're going to have y equals a times the absolute value of x minus h, and then plus or minus k. So just like we did in the last lesson, we're going to kind of examine in these 3 different parts what happens if we change a, h, or k. So in this first part right here, part A, we're going to focus on what happens when you change the k values. So if you notice, our f of x is still our original parent function, and now in g of x and h of x, we're going to see, well, what happens if we put a number on the end? If I put a +1 on the end, or if I put a -1. Let's take a look at what those graphs look like. So if you notice in this picture right here, we have our original f of x function, which is this one right in the middle. Like we said, it's a V shape that goes through 0, 0. So if we start by looking at g of x, when I add 1 to the end, that's this graph right up here. So if you notice, it's still in the same V shape. It hasn't really changed what the lines look like. Our vertex was just moved from 0, 0 up to 0, 1. So what this +1 does is it just shifts the entire graph up 1 unit. If we look at our h of x down here, h of x is down this graph on the bottom. So again, you'll notice that it still maintains that same V shape, except instead of our vertex being at 0, 0, it's now at 0, -1. So the effect that this -1 has is that it moves the entire graph down 1 unit. So what we see in this first part right here is that if I add a value of k to the end, it moves the whole graph up. If I subtract a value of k on the end, it moves the whole graph down. Let's take a look at activity B. So you'll notice in activity B, what we're going to be focusing on changing here is our H value, because we're now putting a number inside of the absolute value symbol. So let's take a look at what these graphs look like here. So again, we'll notice that we still have our original f of x value in the middle. It still has its vertex at 0, 0. If we look here at g of x, when I put a +2 inside of the absolute value bar, you notice that that is this graph over here. So if we compare, the original vertex was at 0, 0, and now it's over here at -2, 0. So how have that graph been changed? It was just moved to the left 2 units. If we look at our h of x graph, when we put the -2 on the inside, that's this graph over here on the right side. So comparing that back to our original f of x function, our vertex was originally at 0, 0, and now it's at 2, 0. So this means that the whole graph was moved to the right 2 units. So again, similar to our quadratic functions, we see that for absolute value, if we put a plus on the inside, it moves it to the left. If we put a minus on the inside, it moves it to the right. And now let's look at the last way that we can transform our quadratic graphs. This is when we are changing the a value, or that coefficient out front. So let's see what happens if we put a negative out front, a 2 out front, or a 1/2 out front. So here's what your graph should look like. Again, we start with our parent f of x function, goes through 0, 0 in our nice V shape. If we start here with the g of x function, when we had a negative, you'll notice that that is this function down here on the bottom. So the g of x function is still a V shape, but the graph is now exactly the opposite of f of x. It's been reflected onto the x-axis. So what we see here is that this negative sign, what it does is it flips the graph upside down. Right? Instead of being an upward facing V, now the whole graph is underneath the x-axis. If we look at our h of x, when we put the 2 out front, I see that that's this graph right here. So you'll notice it's still in the shape of a V, but this V is a little bit more narrow than the original V shape that we have. So the effect that putting this 2 out front has is a vertical stretch. It's almost like I put my fingers on the top and bottom of my graph and I stretched it up and down along the y-axis. Another way of describing a vertical stretch is that my graph is narrower. Narrower means it's closer to the y-axis. And finally, if we compare to j of x, when we put the 1/2 out front, we'll notice again, I still have that V shape here, but my V is not quite as steep. It's a little more smushed or spread out. So the effect that the 1/2 has is a vertical compression, almost like I put my hands on the top and bottom of the graph and I smushed it together. Another way of describing a vertical compression is that it's wider. So again, here we can see that the a value can do 3 things. If it's negative, it reflects upside down. If it's a number greater than 1, such as a 2 that we had in h of x, it stretches the graph vertically. If it's a number between 0 and 1, like a small decimal or fraction, like 1/2 that we had in j of x, our graph is compressed or a bit wider. So if you take a look at the top of page 2, you'll notice this chart hopefully by now starting to look very familiar. Our fourth type of function that we're learning about now is the absolute value family. We see that our original absolute value parent function is the absolute value of x, or in a more detailed form looks as this. Our original graph of the absolute value of x, like we mentioned in our do now, is a V shape that has a vertex at the origin. Its domain is all real numbers, because I can put in any number for x, and its range is y is greater than or equal to 0, because all the y values are 0 or above. And again, you can see in your chart here, there are 3 different ways that we can transform our absolute value functions. Our k value on the end, if our number is added, that shifts the graph up. Subtracting shifts the graph down. Our h of x here inside of those absolute value bars, if it's negative, shifts the graph to the right, positive shifts the graph to the left. And finally, our a value down here can do one of three things. If it's negative, our graph becomes upside down, or it's reflected across the x-axis. If it's a number greater than 1, such as 2 or 3 or 4, our graph becomes narrow or vertically stretched. And if we have a number between 0 and 1, which we know means a small decimal or a fraction, our graph will become wider or more vertically compressed. So hopefully you're seeing the connections between this function family and quadratic functions. Their graphs and transformations work in the exact same way. So let's take a look at our guided practice. Here we're being given the function f of x, which is our parent function, and then k of x, which is our new function. So in our new k of x function, we see that our value of a out front is -2. We see that our value of h here inside of our bars is -3. And we see that our value of k on the end is +4. So let's start by identifying these transformations. Because our a value is -2, that actually will do two things for our graph. The negative sign will cause our graph to be upside down, or a more formal way of saying that is reflected across the x-axis. And because it's been changed to a 2, which is a number greater than 1, our graph would also look more narrow. So the graph would become narrower, and another way of describing that is a vertical stretch. So A has two different transformations here. The negative flips it upside down. The 2 makes it more narrow. If we look at our h inside of the absolute value bars, since it is a -3, that means that our graph is being moved to the right 3 units. And finally, because our k value is 4, that means that our entire graph is being moved up 4 units. So there were 4 transformations that k of x had on our original function f of x. And just to compare our vertex, which again is our turning point, or in this type of graph, it's kind of the center of that V shape. The original vertex of our parent function f of x, we know would just be 0, 0. And if we were to graph this new k of x function, you would see that its vertex is at 3, 4. So how has the vertex been moved? Well, if I went from 0, 0 to 3, 4, that means that my vertex has been moved to the right 3 and up 4. So you'll notice that those left to right, up and down transformations affect the vertex as well as the entire graph. So let's take a look at our checkpoint question. Please try to pause the video here and try this question by yourself. They want you to describe all of the transformations of how this graph has been transformed from the parent absolute value function, which again would be y equals the absolute value of x. So please pause this video, try this question, and then come back to check your answers. Okay, for your checkpoint, you should have identified 4 different transformations. This -1 out front does 2 different things. Because it is negative, it reflects across the x-axis, or you can just say that the graph is upside down. Because this is a 1/2, 1/2 is a small decimal number between 0 and 1, so your graph would be wider, or another way of saying that is that it has been vertically compressed. Moving over to our value of h, because this was a +1, that moves the graph to the left 1 unit. And finally, because we have a -3 as our k value on the end, that moves the graph down 3 units. So there were 4 different transformations that k of x had on our original parent function, which is the absolute value of x. So for our practice for today, if you weren't able to identify any of those transformations or only got one of them, please start with the red problems. If you were able to get either 2 or 3, so you were missing 1 or 2 of the transformations, start with yellow. And if you were able to get all 4 transformations, please start with green. No matter what level you're on, everyone should notice that you're now able to do 4 more problems in your Regents packet that have to deal with absolute value functions. So right now, please pause this video, go try these independent practice problems, and then come back to check your work. Okay, taking a look at our answers here, feel free to pause the video to check your work. Here's numbers 1 and 2 on page 2. Here's 3, 4, and 5 on page 3. Here are 6 and 7 on page 3. Here is 8 and 9 on page 4. Here is number 10 on page 4. So if at this point, if you have any questions about this lesson, please contact us for extra help. To finish off this lesson, you should be going over to exit ticket 9.2 and trying question number 1. And please note that you are also able to answer questions numbers 1 and 2 on homework 9.2 as well.